Usually when we talk about building something massively complex, there's this expectation of a sudden magical transformation.
Oh, absolutely, like a light switch flipping on.
Right. Think about building a house, you know? You have the architectural blueprints, you've checked the zoning laws, you've gathered all the raw materials.
And it's just dirt.
Exactly. It's just a dirt lot. For the longest time, it's just a theoretical concept resting on a piece of paper. But then there's that one specific irreversible moment where the concrete is actually poured.
Yeah, the foundation sets.
And the theoretical blueprint becomes a physical reality that you can literally walk on.
It stops being a description of a thing.
Yeah.
And becomes the actual thing itself, which is a huge mental shift.
It really is. And when you step into the world of compiler design, you spend almost the entire process in that blueprint phase. We've been looking at this abstract diagnostic landscape for so long.
Right, the syntax trees, the symbol tables, lexical analysis, all of that.
Yeah, all the theory. But today we're finally pouring the concrete. We are exploring the final stage of building a compiler, which is code generation.
The absolute definition of where the rubber meets the road.
It is. This is the exact moment where your high-level abstract code is translated into raw, machine-executable assembly language.
And it's a fascinating process to unpack.
So for our mission today on this deep dive, we are unpacking a stack of course materials you've shared with us, specifically the Class 25 notes and Chapter 11 of the textbook Introduction to Compilers and Language Design by Douglas Thane.
A really fantastic practical guide.
It is. We're going to explore the specific mechanics of generating x86 assembly code. And perhaps most surprisingly, we're going to understand why the author deliberately chooses a naive or highly literal approach to doing this.
Rather than a highly optimized one.
Yeah.
Which catches a lot of people off guard.
Right. So you are going to learn the deepest secrets of how the code you write actually commands a computer's physical hardware.
But to appreciate the gravity of that moment, I mean, we really have to look at the immense amount of preparation that gets us there.
Yeah.
If you trace the compiler assembly line from the beginning, the sheer amount of foundational work is just staggering.
I was actually looking at that pipeline in the notes, and honestly, it made me wonder why we need so many distinct steps before we even touch the assembly code.
It seems like overkill at first glance.
Right, because we take a raw character stream, the scanner chops it into tokens, the parser checks the grammar and builds the abstract syntax tree, the AST.
Yep.
Then the semantic routines do all the static checks, making sure variable types match up. Why spend so much time analyzing and rearranging the text just to translate it?
Because the target language, the processor's actual assembly language, is incredibly profoundly simple.
Meaning it's dumb.
Basically, yes.
Yeah.
A CPU doesn't understand abstract concepts like objects or nested loops. It understands extremely granular commands, like moving a tiny electrical charge from one microscopic slot to another. So if your compiler is going to issue those microscopic commands, it needs a perfect, flawless map of the program's logic first. And the AST is that map.
But way Chapter 11 translates that map is fascinating to me. Douglas Thane advocates for what he calls a naive approach.
He does.
He states, we should consider each element of the program, like every expression, every statement, in total isolation, ignoring the surrounding context.
Treating each piece as a standalone unit.
Right. And the best way I could conceptualize this was imagining translating a novel from English to Spanish, literally word for word, without ever zooming out to look at the context of the whole paragraph.
Oh, that's a great way to think about it.
Because if you do that, the resulting sentence might be grammatically clumsy in Spanish. It might take 10 words to say what could have been elegantly said in 3.
It's conservative and it leads to very bloated code.
Exactly. It feels so inefficient.
The analogy holds up beautifully. I mean, a literal translation completely misses the nuance. But you have to consider the constraints of the environment.
Which is an undergraduate class.
Right. In the context of a one-semester course, time is your most precious, limited resource.
You can't spend 3 weeks teaching a system to be eloquent if it doesn't even know how to speak yet.
That is the core philosophy right there. Douglas Thane points out that getting a working, unoptimized compiler across the finish line, actually generating functional assembly language, is a massive victory in itself.
Just getting it to compile is a win.
Exactly. Optimization, which is Chapter 12 of the book, by the way, can only happen once that foundational literal translation actually works.
So the naive approach isolates the variables.
Yes. You build the clumsy translator first so you can clearly see the underlying mechanics of the hardware.
Well, let's talk about those hardware mechanics because the notes give us a real crash course in what our target language actually looks like.
The assembly language.
Right, assembly language is tied directly to the CPU's built-in instruction set. And the textbook focuses on the x86-64 architecture, which is a family of processors known as complex instruction set computers, or CISC.
And a CISC architecture features hundreds of very specific, highly specialized hardware instructions.
Which, I'm not going to lie, sounds completely overwhelming.
It does. But the notes reassure us that for general programming, you really only need to know about 20 of them to get by.
Oh, that's a relief.
Yeah, but to understand those 20, we need to break down the vocabulary.
Okay, so the notes highlight 3 core concepts: directives, labels, and instructions. Directives always begin with a dot, like .data, .string, or .global. What is a directive actually doing?
So directives aren't actions for the CPU to perform at all.
Wait, they aren't.
No, not at all. They're basically informational notes provided to the assembler or to downstream tools like the linker or the operating system.
Oh, okay, so it's metadata.
Basically, when you use docstring, you're telling the assembler, hey, I am defining a string of text here in memory. A .global directive says this symbol should be visible to other files outside of this specific program.
Got it. Then we have labels which end with a colon, like main colon or .lc0 colon. I assume these are just signposts.
Spot on. They're markers for specific locations in the physical memory.
Okay.
And local labels generated by the compiler usually start with a dot, so they don't clash with anything else. But functions and variables from your original high-level code, like main, retain their names as labels, so the operating system knows where to start the program.
Makes sense. And finally, we have the instructions. These are the actual action verbs, the commands telling the CPU to manipulate data.
The real heavy lifters.
Right. But looking at the examples in the textbook, something jumps out immediately. pushHQ, movq, subq. Why are assembly instructions traditionally written in all capital letters? It looks like the computer's aggressively yelling at us.
I get that a lot. It's entirely a visual convention, actually. Assembly language is not case-sensitive at all.
Oh, really? I had no idea.
Yeah, programmers traditionally use uppercase for the instructions because, well, when you're staring at a massive, dense wall of text filled with registers, immediate values, and base relative memory addresses.
It all blurs together.
Exactly. Having the action verbs in uppercase helps them pop off the screen. It makes the code scannable for the human eye.
That makes a lot of sense. Let's trace a concrete example to see this vocabulary in action.
Let's do it.
On page 150, there is a tiny one-line C program, just a main function that executes print hello world with a new line.
The classic starting point.
Always. But when that gets compiled into assembly, it balloons into a huge block of text. The very first thing we see is a directive .string hello% assigned to a local label .lc0, then .string world assigned to .lc1.
What you're seeing there is the compiler organizing the data.
So it's separating the ingredients from the recipe.
That's a great way to put it. It has ripped those strings completely out of the execution logic and stored them in a separate data section of the program's memory. And it gives them those .lc labels so the CPU can find them later when it actually runs the code.
Then, down under the main colon label, the yelling starts. The actual instructions.
Here comes the uppercase.
Right. We see movq, $.lc0, comma %RDI. It's moving the memory address of our first string into a hardware register. It literally takes this one little printf statement and shatters it into a dozen granular individual microsteps.
Which introduces the most critical, delicate part of code generation, which is resource management.
Because memory is tight.
Exactly. Knowing the vocabulary is the easy part. The real trick is how different functions share the CPU's extremely limited workspace without destroying each other's data.
The CPU only has a handful of these fast little memory slots called registers, and the notes introduce a very strict rulebook called the System VABI Register Assignment.
Right, the ABI.
Which stands for Application Binary Interface. This rulebook divides the registers into 2 distinct categories: caller saved and Kali saved.
And the central conflict here is this. When one function stops what it's doing to call a second function, who is responsible for making sure the data currently sitting in the CPU registers doesn't get completely overwritten by that second function?
I was trying to map this to the real world, and it feels exactly like borrowing your roommate's car.
Oh, I like where this is going. How does the contract work?
Well, if a register is designated by the ABI as Kali saved, That means the function being called the person borrowing the car is responsible for preserving it.
Okay, right.
So if I borrow your car and I move the driver's seat, adjust the mirrors, change the radio station, I am contractually obligated to put every single dial back exactly the way I found it before I hand the keys back to you.
That's a very polite roommate.
Right. The caller, the owner of the car, can safely assume their presets are perfectly intact.
The analogy is spot on. Conversely, if a register is designated as caller saved, the owner of the car knows that whoever borrows it is absolutely going to mess with the settings.
They're going to blast their own music.
Exactly. And the borrower has zero obligation to fix them afterwards. So if the caller wants to keep their specific radio station, they have to write it down, save it to their own memory space before handing the keys over.
It's a strict social contract, just enforced at the hardware level.
And without that strict contract, a program would completely lose its mind during execution.
How so?
Well, imagine a function returns, tries to pick up where it left off, and finds all its variables replaced with garbage data from the function it just called. It would just crash.
That sounds like a nightmare to debug. So to prevent that, the compiler has to generate a very specific sequence of instructions every time a function starts and ends.
Yes.
The notes call this the function call template. But to understand it, we need to wrap our heads around what a stack pointer actually is, because the notes show the CPU doing this intricate dance with the physical memory.
Memory in a running program is heavily segmented.
Okay.
You have a massive pool of RAM. A pointer is really just an address, like a house number, pointing to a specific location in that RAM. The stack is a specific region of memory used for keeping track of function calls and local variables.
But the textbook notes something really counterintuitive here. It says the stack grows downwards in memory.
It does.
And when a function wants to allocate space for its local variables, it uses an instruction to subtract from the stack pointer. Subtracting to add space just feels totally backwards to me.
I know, it's weird. Think of the physical layout of your computer's memory like a cave.
Okay, a cave.
The stack is stalactite hanging from the ceiling, starting at the highest possible memory addresses and growing down.
I see.
And the heap, the memory used for long-term storage, is a stalagmite growing up from the floor, starting at the lower addresses.
Wow. Okay, so by subtracting from the stack pointer, you are moving the pointer further down the stalactite, closer to the floor, which exposes more empty rock above it to write data onto.
Precisely the visual. So when we look at the function call template on page 162, the prologue of a function begins the moment it is called.
Right.
The very first instruction is pushQ%RBP. It takes the old base pointer, basically the bookmark of the function that called it, and pushes it onto the bottom of the stack to keep it safe.
Then it executes mufq%RSP, %RBP. It copies the current stack pointer into the base pointer.
Yes.
It's essentially staking its claim, saying, this spot right here is the new foundation for my local memory.
Next, it does that subtraction we just talked about, subQ $16, comma, %RSP. It drops the stack pointer down, allocating empty space on the stalactite for its own local variable.
Right, making room.
And finally, it pushes any of those Kali-saved registers to the stack. It's formally taking inventory of the roommate's car settings so it can restore them later.
I love that. And once that prologue is finished, the function actually does its assigned work, the math, the logic, whatever we programmed it to do.
The actual meat of the program.
Right. And when it's finished, it performs the exact reverse of that dance. The epilogue.
The teardown.
Yeah. It pops the Kali-saved registers back off the stack, restoring the mirrors and the radio. It forces the stack pointer back up to the base pointer, instantly erasing its local variables. It pops the old base pointer, returning to the previous function's bookmark. And finally, it calls retbeh to physically return control to the caller.
And as a compiler writer, your job is to write the C code that automatically generates those exact assembly instructions for every single function in the abstract syntax tree.
Which brings us to the playbook. How do we actually traverse that AST and spit out the assembly?
Well, Chapter 11 lays out a hierarchical set of functions. It essentially mirrors the tree structure.
Okay.
A function called declcogn handles declarations. Inside a declaration, there are statements, so it calls stmtcogn. Inside a statement, there are math and logic expressions, so it calls exprcogn.
And it relies heavily on a concept called post-order traversal.
It does.
I understand that post-order traversal means visiting the children of a node before visiting the parent. But physically, mechanically, why is that required for code generation?
Consider an abstract syntax tree node representing an addition operation. It has a left child, say the variable a, and a right child, the variable b.
Okay.
The CPU physically cannot add two numbers until the electrical signals representing those specific numbers are resting in the physical register slots of the processor.
Right. It needs the data first.
Exactly. If you try to visit the parent node first, you're commanding the CPU to add empty air.
It's like reading a massive algebraic equation from the inside out. You have to resolve the deepest set of parentheses first. You gather the raw ingredients, load them into registers, and then you trigger the addition circuit.
What complicates this is that sometimes the AST is actually a directed acyclic graph.
Okay, you're losing me at directed acyclic graph.
It sounds intimidating, but it simply means a tree where some branches share the exact same leaves.
Oh, okay. Like a shortcut.
Sort of. Imagine an expression like a plus b times a plus b. Instead of calculating a plus b twice, an optimized graph will point both sides of the multiplication node to a single a plus b subtree.
That's clever.
It is. But whether it's a simple tree or a DAG, the post-order traversal ensures the assembly instructions for evaluating the bottom of the structure are printed out before the instructions for the top.
But this immediately brings us back to the limited resource problem we mentioned earlier. If we are constantly loading these leaves into registers, how do we keep track of which registers are currently holding our ingredients and which ones are empty?
This is where Douglas Thane introduces the functions scratch lock and scratch free. And true to his philosophy, his mechanism for managing these scratch registers is unbelievably simple.
The notes show a table on page 182. It is literally just two parallel arrays.
That is the entire tracking system. One array is an integer array of zeros and ones, representing whether a specific register is in use or not. The other is an array holding the actual text strings of the register names, like %RBX, %R10, %R11.
So when our traversal hits the variable A, it calls scratch lock. That function just scans the 0-1 array, finds the first 0, flips it to a 1, and returns the register number.
Yeah, say register 0.
Right. Then the compiler emits the instruction MOVQA, %RBX.
And when that value is finally consumed by the parent addition node and is no longer needed, the code generator calls scratch free on register 0.
It flips the 1 back to a 0.
Exactly, making it available for the next calculation.
It is incredibly elegant. But there is a glaring flaw staring at me from the note.
Oh, I bet I know what it is.
That table only lists 7 scratch registers, registers 0 through 6. What happens if our post-order traversal hits a massive, convoluted math equation?
So think deep.
Yeah, something with 15 different variables that all need to be held in memory before the final operation can happen. We simply run out of scratch registers.
That is the exact limitation the author wants you to discover. If you look at the exercises at the end of Chapter 11, Exercise 1 asks you to deliberately write a legal expression that exhausts the available scratch registers.
Wait, so the compiler just crashes?
Under this specific naive implementation, yes. Because we are evaluating every expression independently, holding all intermediate values in registers without saving them, a deep enough tree will run you completely out of physical hardware slots.
How does a real-world compiler solve that, then?
An optimized compiler detects when it's running out of registers. It generates instructions to temporarily spill some of those values out of the registers and push them onto the stack in memory.
Freeing up the register for the immediate calculation.
Exactly. And later, it generates instructions to load the original value back from the stack.
But implementing register spilling requires the compiler to have a complex awareness of the whole program, right?
Yeah.
To know which values are safe to spill and which are needed immediately.
Which completely violates the foundational rule of this chapter, treating everything in isolation.
Right. For the scope of a one-semester course, Thane's simple 0-1 array is sufficient to compile most reasonable test programs. It illustrates the concept perfectly without burying the student in edge cases.
And knowing that these registers will inevitably run out, and knowing the boundaries of this naive approach is exactly the wall you are going to hit when you sit down for Lab 10.
Oh, absolutely.
Looking at the course roadmap, Lab 10 is the code generator. It is the culminating technical challenge of the semester.
And when you sit down to write Lab 10, that blinking cursor on a blank screen is going to look terrifying.
I can imagine.
You're bridging the gap from a human-readable distraction all the way down to executable reality.
But Appendix A of the book gives you a secret weapon to conquer that blank screen. It explicitly states, do not worry about efficiency yet. Start with extremely simple programs. Start with return 2 plus 2.
Trace the life cycle of 2 plus 2. Think about what a monumental achievement it is just to make that run. Right. If you can get your C code to parse 2 plus 2, traverse that tiny 3-node AST, Call scratch-lock twice to claim 2 registers.
Emit the string text to move the 2s into those registers.
Emit an ADDQ instruction to add them together, and then wrap all of that inside the push queue and pop queue dance of the function call template. You have succeeded.
The operating system will physically execute your program.
It's incredible.
You stop analyzing language and you start commanding the machine. Let your initial code generator be naive. Let it produce clumsy, bloated assembly. Getting the architecture functioning is the entire point.
So let's retrace the path we've walked today. We started with the abstract syntax tree, the theoretical blueprint of what our software is supposed to do.
Yep.
We learned the raw vocabulary of the x86-64 architecture, distinguishing the directives from the all-caps instructions. We explored the physical memory cave, learning how the stack pointer subtracts to grow downwards.
The stalactites.
Right, the stalactites. We uncovered the strict social contract of the caller and Kali saved registers.
And we broke down the playbook. We saw how a post-order traversal ensures the deepest leaves of our logic are loaded first, and how a simple binary array can manage our limited scratch registers, embracing the deliberate limitations of a naive approach.
It fundamentally changes how you look at the tools you use every single day, which leaves us with a final thought for you to mull over.
What's that?
Well, once you actually build this translator, once you generate code naively and see how bloated, literal, and repetitive the resulting assembly language is, you realize just how much invisible, heavy lifting modern compilers are doing behind the scenes.
Oh, completely.
When you compile a program with something like GCC today, it is not being naive. It is doing intense context-aware optimization. It is spilling registers, reordering instructions, and collapsing DEG.
It's basically performing magic.
It is. So the question becomes, how much faster could the software of tomorrow be if we truly understood the mechanical realities of the hardware it runs on today?
That relentless pursuit of efficiency is really what drives the entire field of compiler design.
And now, you have the foundational knowledge to join that pursuit. Thanks for exploring the depths with us.